All right, we're going to finish up talking about electricity and magnetism in this course by talking about AC power, RMS values, and transformers. And we're going to begin this way. In any sort of an RLC circuit, the alternating current generator is the source of energy here. And the energy is provided by that source, and it is stored in the electric field of the capacitor and the magnetic field of the inductor. And it gets dissipated away as heat by the resistor. So the LC is what causes the oscillation, and the R dissipates away energy. And it dissipates away that energy at a rate of I squared R. So the source is supplying the same amount of energy that is being dissipated away. The average energy in the inductor and the capacitor is constant. It stays the same, but to replace the energy that's dissipated away, the generator fills in that space. All right? The energy that's dissipated away by the resistor then is power, I squared R. Now, we know what I looks like for an AC circuit. It looks like capital I times the sine of omega t minus phi. So take that right there, square it, and multiply by R. We get out I squared big R times sine squared omega t minus phi. There, that's what the power looks like. If you were to graph that, let's say we graph, this is time here versus power. And let's make this point right here, capital I squared R, right there. Well, what's that look like? At t equals 0, this is going to be 0. So it does this. And rather than going below down here, the way that a normal sine function would, this is a squared, so it just goes back up like that. And it's going to continue on with that cycle like that. Okay, so this is the power. Now this right here is the instantaneous power. In other words, at any particular time that you pick, the power itself could be 0, it could be I squared R, it could be any number in between, depending upon what time you choose. So the instantaneous power is only good if you need to know the power at a specific time. What's more useful, though, is going to be the average rate at which energy is used up by the resistor or dissipated by the resistor. The average rate is much more useful then. What is the average? Well, P average is going to equal, well, it's going to be this, but we need to average this over time. Well, the I doesn't change, capital I doesn't change, R doesn't change over time. The only thing that's time variable here is the sine curve, and it's specifically a sine squared. So if we just look at the sine squared here, it's going to range between 0 and 1. Because it's a squared. It goes from 0 to 1 without the coefficients out front. It's just going to, the sine squared itself is going to be between 0 and 1. So the average of that is going to be a half. So 1/2 times I squared R, that would be the average power. Okay, we can rewrite that. Let's take that. P average is equal to 1/2 I squared R. And let's play a little math trick here with it. Let's write it this way. Let's take the 1/2 here, and I'm going to put it underneath this, and now square that. Okay? What I've done here is I've created something called an RMS value. So this is an RMS value for current. So current itself, I RMS, that's kind of like an average value for current, is equal to capital I, that's the peak value, divided by square root of 2. Now that's a definition of what an RMS value is. How did we get that? Well, we started with I, that's the peak value. Then you square that, and then that's the square part. Then you take the mean of that. That's where the 1/2 came in when we took the average or the mean. And then you take the root. So we've got I over square root of 2 then when we take the square root of that. And that is the RMS value, root mean square. So you can think of this as kind of an average for current, because current itself, if you'll think about current as capital I times the sine of omega t minus phi, what's the average of this? The average of that is 0. Because if you graph it, it goes up to some maximum and down and up and down. And that maximum is capital I. And down here, the minimum is going to be minus I. So you go through this oscillation, and what's the average of that? Well, split it right down the middle, that's 0. So the I here is, the average of this I is going to be 0. It's much easier to talk about the RMS value rather than talking about the average of the instantaneous, which is going to be 0. So IRMS is also useful in this way. Notice the power equation now becomes IRMS squared R. And that's a form of the power equation that you're used to. P equals I squared R. So if you use RMS values, then you can stick with the old faithful equations that you know. So power equals I RMS squared R. It's also equal to E RMS squared over R. That's V squared over R. Or it's equal to I RMS times E RMS. That's P equals IV. So these are the old faithful power equations that you're used to. Also, the other equations like I RMS is equal to E RMS over R if you're talking about a resistor, or Z if you're talking about an impedance. So the old faithful Ohm's law works if you stick with RMS values. Okay, so I'm showing you this. The average power then is just I RMS squared, like that. Okay, but we can write that a slightly different way, and it'll be more insightful to see that happen. Okay, first of all, I RMS is equal to E RMS over Z. And the average power is equal to I RMS squared R. So if I take this I RMS squared, I could break that into something that looks like this, just I RMS multiplied by I RMS times R. That's not a surprise. But I can now substitute in for one of these I's as E RMS over Z times I RMS times R. Now, just rearranging the terms a little bit, I've got E RMS times I RMS times R over Z. This term right here, R over Z, is called the power factor. Now, R over Z is actually equal to the cosine of the phase angle. Now, that's not obvious that that's the case, but let me convince you that that is indeed the case right here, right now. Let's go back to our phasor diagram. For a phasor diagram, we have an I going off in that direction, which places V sub R right on top of that. And then we had, going off in this direction, we had V sub L minus V sub C, those phasors. And the E vector was the resultant of these two right here. So this is E sub m. That's the E vector. Now these angles are kind of important to us here. First of all, to here, back to here is omega t. But from, let's say, here back to here is omega t minus phi for the I. So this is the angle of the EMF vector. This is the angle for the current vector. And that makes the angle between these two right here phi. All right, now look at this triangle here where phi is. The cosine of that angle is going to be adjacent over hypotenuse. Well, the adjacent is V sub r. The hypotenuse is E sub m. So we can write V sub r, that's capital I times r, divided by I times z. The i's will cancel, and we're left with r over z. And that is the power factor. So these two things right here are equal to each other. Now, that's the way the average power can be written then. We have power equal to E RMS, this is average power, I RMS times the cosine of the phase angle. And it is the cosine of the phase angle that is known as the power factor. Okay, now that's kind of insightful, because if you are a power company and your goal is to maximize the power, to get the maximum amount of power to customers, then you want this cosine phi term to be 1. I mean, that's the maximum it could be, is 1. But from trig, you probably recognize that cosine of phi is the same thing as cosine of minus phi. So the sign of phi doesn't really matter. It doesn't really play a role here in the power factor because of this trig identity here. But what you want is you want to get cosine of phi equal to 1 so that if you're the power company, you can get the maximum power to people. Well, when does that happen? That happens when phi is 0 degrees. All right, which means that r over z, which is the same as cosine phi, is also equal to 1. Okay, what does that mean? That means that you're going to have maximum power when R equals Z. So when the resistance is equal to the impedance, this is called an impedance matching. So you want to match impedances here. Okay, let's go ahead and substitute in R equals Z, but we know that Z is equal to the square root of R squared plus X sub L minus X sub C quantity squared. When is this a true statement? In other words, we know that this is the condition that we want in order to maximize the power factor, but when is that the case? Well, look here. Look at this equation. If what's in the parenthesis here is 0, in other words, if X sub L is equal to X sub C, then this is a true statement, that R equals R. So if we want to maximize the power factor, we need to make sure that X sub L is equal to X sub C. Well, what does that mean? We're carrying it a step further. Well, X sub L is omega L. X sub C is 1 over omega C. So where is this going? Right back where we started. In other words, the power company wants to have their generator frequency equal to this, which you recognize as the natural frequency of the system. So a power company, let's say over here, this is the power company, that's the generator. Here's the smokestack, there's smoke coming out. They're generating power over there. But over here is the user. That could be you at your house, it could be an industry, it could be a number of things. But there's a distance between here and here. Let's say that distance is 1,000 kilometers. Okay, you have to take the energy that's generated over here at the power plant and deliver it over here. Well, how do you do that? Well, you take maybe a couple of long wires and you string it like that. And then you got these power poles that are out here. Maybe they look something like that. Okay. All right, but the point is you have to deliver it from there to there. Well, all along this path right here, there is resistance in the way. And this is a network. Even though I just drew it as a couple of lines here, this is actually an entire network of power lines. And a network, anytime you have something like that, it has a natural frequency. And you're putting oscillating currents into it, alternating currents into it. So what needs to happen is that the generator frequency, which is set to 60 hertz, that's an omega of 377 hertz. Okay, that implies an omega of 377 hertz. That this is pretty much set by standards in the United States to be 60 hertz. However, the network itself has a natural frequency at which oscillations will occur within it, and that is omega naught. And that's 1 over the square root of LC. So if you can go into your network and you can balance it so that it has a natural frequency equal to the frequency of the generator, then you're going to maximize your power factor. So that's the way you do it. I mean, literally, a power company will go out and insert devices into the line to adjust inductance and capacitance. And those devices then will change the natural frequency of the system to match the frequency at which the generator, and when that occurs, you maximize cosine of phi, which maximizes the amount of power that can be delivered, the average power that can be delivered. Okay, so that's one of the goals of a power company, is to balance this network. Okay, but there's another goal for the power company. It is to have a power factor of 1, but there's more to it than just that. Let's keep this up here so that we can look at it right now. Let's say electricity is sent out from the power company. In this case, it is 735 kilovolts. Those are some of the big towers that you'll see carrying power lines cross country, transmission lines. To a customer that is 1,000 miles away, that's a reasonable voltage to have. Now, let's also suppose that the power company has gone out and they have balanced the network and everything is just perfect, that we have a power factor, a cosine of phi that is 1. Okay, that's a desired thing for the power company to do. All right, let's also assume that there's a current present here, and that current is 500 amps. It's a lot of current. Okay, then the average power that's going to be delivered by the company. In other words, the generator over here is going to generate a power P that has an average of I times E. Okay, well this is I, this is, I did that completely backwards. This is I, this is E. You get the idea. Okay, so what have we got? We've got I equals 500 amps times E, 735 times 10 to the third volts, gives me an average power of 368 megawatts. Okay, that's the rate at which energy is supplied by the power company. Okay, that's how much power it could potentially deliver as long as there's no loss along the way. That's the energy coming out of the generator. All right, but we know that along this path right here, there's a lot of wires. Even though it looks kind of like a short distance here, there's a lot of wire there. And maybe there's a little bit of resistance in the wire, because we've assumed resistanceless wires for most of the semester. Doesn't mean that wires don't have resistance, it just means we've ignored it. But let's say that there is a resistance associated with this wire of 0.220 ohms per kilometer. That's a very small amount of resistance. And we have Between the generator and the user, we have 1,000 kilometers, so that means we have a total resistance of, move the decimal place over 220 ohms. Now that's a small amount of resistance for an entire network, but I want to show you why that's important. The average power for this is I squared R. The current that's going through these power lines is 500 amps. Square that, multiply by 220 ohms, and you end up with 55 megawatts. What is that? That's how much energy is lost due to the resistance of the wires. So remember, heat is dissipated by the resistance of the wires at a rate of I squared R. As long as we're talking about RMS values, and by the way, I haven't been real careful about this. All of these are RMS values, all right? But look, we have 55 megawatts of power lost of the 368 that's produced. So if you take 55 divided by 368, that's 15%. That means you have a 15% loss of energy from the supply rate. Okay, so you're losing 15% of your electricity on the way. Okay, so how do you get that back? Well, we've seen that the power company needs to balance the network to produce a power factor of 1 in a perfect world. This is what we want in a perfect world, and that's what the power company strives for. But the other problem is the ohmic loss. Okay, this is ohmic loss. Ohmic loss due to just the nature of resistance when you pass a current through it, that you have energy lost at a rate of I squared R. And in this case, it's 15%. So wouldn't it be great if you could somehow reduce the ohmic loss? Well, how do you do that? Well, the ohmic loss is due to I squared R. It's due to this I squared R. If there's a way that we could either make the resistance smaller, and maybe we can, but this is a tiny resistance already. Maybe you could have superconductors that have no resistance, and that would be awesome. Of course, superconductors that are able to operate at temperatures of room temperature are a fantasy at this point. So that's probably not an option, reducing the resistance. What if you reduce this? What if you could make the current smaller? In other words, the power company does the generating over here. What if they just shipped it out at a very small current? If they shipped it out at a very small current, then the ohmic loss is going to be dramatically different, because this is an I squared. So you make I half, then the power becomes 1/4 the ohmic loss becomes 1/4 of what it was, because you have made I just half of what it was, and it's a squared relationship there. But how do you do that? Well, there is a way to accomplish that, and the device is a transformer that allows that to happen. You see, here's the rule. I'll go back to this picture one more time. You're getting tired of seeing it. Here's the rule. The power company wants to transmit at the highest possible voltage and the lowest possible current, because it is the current that causes the ohmic loss. So you want to transmit at lowest possible current, which means, because these two things are a balance, you have a high voltage. So high voltage, low current. That's what they want to transmit at. But the user on this end, that creates a problem for them. Because, you know, maybe at your home, you need several amps to turn motors in your refrigerators, or motor on your whatever device you have that has a big motor on it. Now this would really be a problem for an industry. If the industry has large motors, then they need lots of current in order to turn the motors over, to keep them running. So The users over here may need much larger currents than what the power company is willing to transmit, because the power company is going to lose due to ohmic losses. So transmit power from the generator at the highest possible voltage and lowest possible current, but on this end you want just the opposite. You want a larger current and smaller voltages. Okay, wouldn't it be great if there was a device that allowed a power company to do that, transmit at high voltages but low currents? And there is. And that's a transformer. And that's what we need to talk about now. A transformer can be thought of this way. Now, transformers themselves are fairly complex devices these days, but they all work off of the basic principle of transformers. What I'm drawing here is a rectangle of some magnetic material, let's say iron. So all of that right there is solid iron. And it's got some thickness to it here that I haven't really drawn. But this is a chunk of iron. Now, over here on this side is the power company and all the power lines and everything. So there's your source. And then we take wires from the power company and we come over here and we wrap them around this side. So they come out, they go around, come out, go around, come out, go around, like that. And then back to the generator. Okay, now this side over here is the side that faces the EMF generator. So we're going to call this the primary side. And of course that means this side over here has to be the secondary. Now, what we've done here is we've wrapped some wires around this iron core. And since this is the primary side, let's call this number of turns N sub P. That's the number of turns on the primary side. Okay? And this is an EMF generator that's going to generate a sinusoidal voltage given by E equals E sub M sine omega t, like that. Now, over here on the secondary side, we're also going to do what we did. We're going to wrap some wires around over here, over here, over here. And then this is what's connected up to your house. Your house may be a business or an industry or something, but we're going to symbolize it as just a load. So this is a resistance. That resistance symbolizes everything that's inside your house or everything that's inside the business. And we're going to call it the load resistance. So subscript L there indicates that that's a load resistance. All right, so we've got this iron core. We've got some windings on each side. And on the secondary side here, we would have N sub S windings. And we've got two coils connected by the iron core. The coils themselves are insulated from the core, so they're not actually, electrically in contact with the core, but they are wrapped around. So they're insulated wires wrapped around. Okay, now there is a relationship then between the power, the current, the voltage, the resistance over here on the primary side to what's on the secondary side. Okay, it's not exactly the same. We assume that resistances on these windings are negligible. So we're once again assuming that our wires themselves have no resistance, or we're just interested in what's happening inside this device here, inside the transformer. Okay, well, think about this. This is an oscillating voltage source, so it's going to create an oscillating current. And this is a coil wrapped around an iron core. So what's going to happen when you have a current going through this iron, these wires, is going to create a magnetic field. And that magnetic field is going to oscillate back and forth inside this because of the oscillating source. So we're going to have a magnetic field going back and forth, back and forth, back and forth here inside the iron core. Well, because it's connected to this iron core, and iron is magnetic, then any kind of magnetic field set up over here is instantly, at the speed of magnetism, which would be effectively instantaneously, that magnetic flux is going to change at the same rate over here. So as quickly as it changes here, it changes at the same over here. Okay, well, a changing magnetic flux then through a coil is going to generate a current. So we have a current that's going to be created over here, a current and voltages that are going to be created over here on the secondary side due to the fact that we have a changing voltage current over here on the primary side. Well, the way to understand this is through Faraday's law. And Faraday's law says that E equals N d phi dt. All right, let's write that a little bit differently. E over N is d phi dt. Well, phi, you may recall, is magnetic flux. And here's the thing you need to keep in mind. As quickly as the flux changes over here, it changes just as quickly over here. So we have almost no delay between the rate of change over here and the rate of change over here. In fact, we could say it's exactly the same. So this d phi dt, the rate at which the magnetic flux changes, is the thing that is constant on both sides. And if that's true for that, then the EMF per turn is going to be the same for both sides. In other words, the EMF per turn on the primary side, we could write that as, let's say, the voltage on the primary side divided by the number of turns on the primary side, has to equal then the voltage on the secondary side divided by the number of turns on the secondary side. So that relationship comes about because of the constancy of the rate of change of the flux, because these two coils are connected by the iron core. Now this is the EMF per turn. The EMF per turn is the same on both sides. So if I rewrite this, V sub S, and you could solve for V sub P, but I'm doing V sub S. V sub S is equal to V sub P times N sub S over N sub P. So we have this ratio here of the turns. Now all of these are RMS values. Everything is RMS value from here on out. If you look at this, and you can see that if N sub P is less than N sub S, then what we have here in this ratio is a number that is bigger than 1. So if that's the case, then the voltage on the secondary side is bigger than the voltage on the primary side. We would call this type of device a step-up transformer. Why would we call it that? Because it is stepping up the voltage. It's going from some voltage over here to a higher voltage over here. All right? And just the opposite, if N sub P is greater than N sub S, then what do we have? Well, N sub P is the bigger number here, N sub S is the smaller number here, so this ratio is going to be a number smaller than 1. So when we multiply by the primary, then that means the secondary voltage is smaller. So this is called a step-down transformer. So you judge whether or not a transformer is a step up or step down based upon whether or not the voltage across the primary is bigger or smaller than the secondary. And it's based upon this relationship. So step up, we are going from voltage on the primary being less than voltage on the secondary, and step down, the voltage on the primary is greater than the voltage on the secondary. So that's how you determine whether or not a transformer is a step up or step down. Now, this leads to some interesting things because it certainly, as you can see, affects the voltage on either side here, but naturally it also affects the current. And it affects the current this way. Based upon conservation of energy, the power on the primary side has to equal the power on the secondary side. That's just a conservation of energy statement. The rate at which energy is supplied or used on the primary side is equal to the rate at which the energy is supplied or used on the secondary side. So that's just a restatement of conservation of energy. Well, on the primary side, we have I sub P times V sub P. That's just P equals IV for the primary side. And we have I sub S equals V sub S. So that has to be the case. Well, what does that mean? I sub S then is equal to I sub P times N sub P over N sub S. So once again, we've got a ratio of the windings on either side of this. Now notice, just to remind you, this is the opposite ratio from this, okay? So as voltage goes up, current goes down, or vice versa, as current goes up, voltage goes down because of the nature of the ratios here. Okay, so you can see then that the current is also transformed from the primary side to the secondary side. Depending upon this ratio, could be greater than 1 or less than 1. The secondary side could have a greater current or a smaller current if it's going the other way. All right. So what would you want? At your house, you would want something that creates a larger current on the secondary side, because you take that current that the generator, that the power company has sent through the network, which should be small, and you want your power to be greater, or your current to be greater. So what do we want? We want more windings on the primary side than the secondary side, so that this ratio is going to be a number bigger than 1, and we get out a bigger current. Okay. All right. Another thing, before we work a problem regarding this, we know that on the secondary side, that I sub S is equal to V sub S over R sub L. That's the load resistance. So if I can make a substitution for V sub S, let's make this substitution right here. And V sub S becomes V sub P times N sub S over N sub P divided by R sub L. All right, now I sub S, I could also make a substitution for that using this up here. So I sub S is going to be I sub P times N sub P over N sub S, and that's equal to V sub P N sub S over N sub P, all that over R sub L. Okay, now let's rearrange the terms here. I sub P is equal to, we've got V sub P on top, I've got R sub L on bottom, and I'm going to write the ratio as N sub P over N sub S, and there's going to be squared there. All right, now I want you to notice this equation has the general form of this equation. In other words, current is equal to voltage over a total resistance. So this is V sub P over R on the primary side. Now here's the point. R on the primary side is equal to N sub P over N sub S squared times R sub L, which is the resistance on the secondary side. So that means that the resistance the primary side sees is different than the resistance on the secondary side. Okay, keep that in mind. The resistance on the primary side and the secondary side are not the same. In the same sense that the voltages on the primary and secondary side are not the same, and the currents on the primary and secondary side are not the same, the resistances are also not the same. All right, so let's work a problem here. Let's say let's suppose that we have a transformer on a utility pole right out front that operates at 8.5 kilovolts, and remember everything's RMS here. So if I forget it, it's still RMS. And let's say the house operates at 120 volts RMS. Okay, so the power coming in, the voltage coming in is 8.5 kilovolts, but we need that to only be 120 volts at our house. Okay. Well, first of all, what kind of transformer do we need? Do we need a step up or do we need a step down? Okay. You should be able to know that. You should be able to recognize that just from what's written here. We need a step down transformer. Now, if we need a step down transformer, and this is V sub P and this is V sub S, then based upon our transformer equation for voltage, then we can say this: we need the ratio of these two to be some quantity. Okay, what does that quantity need to be? Well, the ratio of N sub P, N sub S is going to be V sub P over V sub S. So it's going to be 8.5 times 10 to the third volts divided by 120. So that turns out to be 70.83. So what do we need? We need a ratio of windings in the primary and secondary side that's on the order of about 71. So ever how many windings you have on the secondary side, on the primary side, we need 71 times more that. Okay? So that's the ratio then between the two. All right? Now, let's suppose, let's take it a little bit further. Suppose the house uses 78 kilowatts of power. Then the current in the transformer is going to be, now the power is the thing, remember, that's the conservation of energy. The power is the thing that's the same on both sides. So it's the same on the primary and secondary side. So on the primary side, it's going to be the average power divided by V sub P. This is the average power. Okay. So this is going to be 78 times 10 to the third watts divided by V sub P, and V sub P was 8.5 times 10 to the third volts. This turns out to be 9.2 amps. So that's the current on the primary side. That would be the current that the power company is transmitting through the power lines. Okay, what about on the secondary side? What's the current over there? Well, I sub S is equal to, same thing, P average divided by V sub S. Well, that's going to be 78 times 10 to the third watts divided by the voltage on the secondary side, which is 120 volts. This turns out to be 650 amps. So on the secondary side, you have a lot more current, and that's exactly what we needed. We needed to step down the voltage, but we needed to step up the current. However, whether or not a transformer is considered a step up or step down depends not upon the current, it depends on the voltage. All right, so you identify it by the voltage as a step down transformer in this case. All right, one other thing before we disappear here. What about the resistances? What is the resistance on the secondary side and the resistance on the primary side? Well, we have enough information. I don't have to give you anything else. You should be able to figure this out. R on the secondary side is just V sub on the secondary side divided by I on the secondary side. Well, V on the secondary side is 120 volts. I on the secondary side is this 650 amps. So what is that? 0.18 ohms. A tiny amount of resistance on the secondary side. But what does the primary side see? Remember, the primary side, R sub P, same form of the equation, also works. The primary side sees a different resistance than the secondary side. Okay, so V sub P, that was 8.5 times 10 to the third volts divided by I sub P, which is 9.2 amps. So that turns out to be about 926 ohms. So a significant increase in resistance is seen on the primary side. Now we use this equation to find R sub P. We could have used the other form and we should get the same answer. Let's double check. R sub P should equal N sub P over N sub S squared times R sub S. Well, N sub P, N sub S, that was 70.83. We'll square that and multiply it times R sub S, which is 0.18 ohm. And that turns out to be 926 ohms. So, yep, they match. Okay, so either one of those equations, the Ohm's law form of equation or the transformation due to the transformer equation would work as well. Either one of those. Okay. All right. At this stage, you should have enough information to be able to solve transformer problems and RLC circuit problems. So at this point, I'm going to officially say that we are done with electricity and magnetism. The remainder of the class will be optics. And we'll continue that next time.